next part, I'm going to talk about neural correspondence. So talking about, okay, what are the neural components of this really complex really complex cognitive process and how they contribute to that process. Let's just start with this slide in terms of trying to think about theory of mind and think about, okay, when we talk about theory of mind, what are the cognitive components that are involved if we want to just deconstruct theory of mind to other components? Let's think about deconstructing a complex concept of theory of mind into smaller cognitive processes. And we can start that with, let's say, the eyes task that we reviewed together. So when you have been trying to see what is happening in others' mind based on their eyes, trying to understand, okay, what are the components, what are the processes that are happening right now in my brain to help me to understand what is happening on others' mind. How can you kind of define those components? Let's kind of put those components in the chat space. Now I can see Paria that is mentioning attention. Okay, what are the other processes that are involved if you want to deconstruct theory of mind to other pieces? Okay, I'm waiting. I mean, people are thinking about, okay, what are the components of theory? Based on what we have discussed so far, what are the things that you think that, I mean, what are the elements that could contribute to that? So memory, okay, good, I do agree. Empathy, okay. Face recognition is going to contribute definitely. Emotions. Okay. There are definitely different components involved. Simple components like face recognition. We need to have face recognition to be able to have theory of mind. We need to be able to visually process features. We need to do some initial face processing. Okay. We need to define self, as you have mentioned, defining self from others. We need to have emotion processing. We need to have gaze processing. We need to have an understanding of causality. And causality would be related to intentionality as well. When there is an intention in somebody's mind, then he or she could cause something. So then our understanding about causality sometimes is related to intentionality. And then being able to separate belief from facts. So we understanding that there are people have beliefs that are not always facts. And then defining goals and moral reasoning for others and tracking intention and goal and moral reasoning among others. So as you can see, these components would contribute to, let's say, being able to infer state from eyes. This is the eyes task that we discussed about this. Defining mental states based on the eyes. And then trying to inferring mental states based on the motion. So this is the task that we reviewed before, just some moving objects. And then being able to inferring mental states to human action. So action, defining a specific action, how actions, and then thinking about how we can predict behavior based on the mental state. So it is exactly the Anne and Sally task. So we know you can see that theory of mind could be decomposed in other components, and we need to understand these components to be able to understand what we call theory of mind. Let's go back to the anatomy and review what we have learned so far. If you remember, we have discussed about what we call parahippocampal gyrus. We have discussed about fusiform gyrus. And then we discussed that, okay, fusiform is involved in what we call face area. So this is the left and right fusiform area, fusiform face area. And then we have parahippocampal gyrus that was involved in object recognition. So from face recognition to object. So we know that these components that are critical in terms of being able to help us to recognize faces and objects. And so they can definitely contribute a role in what we call social cognition. Without face recognition, social cognition would not be happening. So we know these components should play a role. Then we discussed about prefrontal cortex and orbitofrontal cortex, and we discussed that dorsolateral prefrontal cortex is representing mental attributions to the future goals or future plans that we have. And when we talk orbitofrontal cortex, it would also be related to the values and rewards and the prediction that we have for values and rewards in the future. So we discussed that these parts are futuristic parts of our brain that would provide mental representation of what is going to happen tomorrow, in the next few minutes, or in the next couple of years. We are just reviewing the anatomy that we have learned so far. I'm just kind of giving you something like a crash course of anatomy, because I'm going to expose you to some other studies, and you need to review the understanding you had from anatomy. And that is the way that I highly recommend people to learn anatomy. Just starting with kind of being exposed to that in a problem-oriented way over time, and over time you develop the skills to be able to understand these complex names and see the variations in terms of the naming and labeling and parceling these pieces in different brain atlases. So we discussed about what we call ventromedial prefrontal cortex, medial prefrontal cortex, dorsomedial prefrontal cortex. I mean, these pieces are dorsomedial, medial frontal cortex, ventromedial. And as you can see here, in this figure, this part is labeled as ventromedial prefrontal cortex. Sometimes people name this part as orbitofrontal cortex, and then a little bit more lateral part as ventromedial prefrontal cortex. So you can see that there is a variation in terms of how these parts are being labeled as ventromedial prefrontal cortex or orbitofrontal cortex. But meanwhile, we have an area that we call cingulate gyrus, this part. There are people who name this red part as what we call paracingulate. So let me just clean this up a little bit. So paracingulate gyrus and then cingulate gyrus. And there are atlases that they call all of them as cingulate. So they name the entire as cingulate. So there is a variation in terms of considering paracingulate and anterior cingulate, or just putting them all together as anterior cingulate cortex. Okay? And then when we talk about, as you can see here in this figure, obviously you can see that the entire is just labeled as anterior cingulate cortex. And then dividing that into sometimes mid-cingulate and anterior cingulate. And then anterior cingulate could be divided to what they call pre-genual and sub-genual. And as I told you, this is called genu, which means knee in Latin, and it's what we call corpus callosum. So because it is something like a knee, so it is called under the knee or in front of the knee. So it would be subgenual or pregenual cortex. Okay? So these are just kind of refreshing your memories, and then getting to the social cognition areas. These are the major areas that are involved in different levels of social cognitive processing. We have, as I told you, dorsomedial prefrontal cortex, what we call temporal parietal junction, posterior superior temporal sulcus, amygdala, fusiform face area, orbitofrontal cortex, ventromedial prefrontal cortex, insular cortex. So these are major parts that playing a role, and each of them would play its own role. For example, these ones are more involved to decision and reward. These parts would contribute to the theory of mind task, especially the eyes task. And then these are some components of social cognition, like intentionality. So different parts of the brain would contribute a role in what we call social cognition. Let me just give you a few examples. One of the dichotomies that we have in terms of when we are in the social cognitive processing, differentiating between affective and cognitive processes. So sometimes we are just involved in terms of feeling what others are feeling and getting involved into the affective processing, okay? But sometimes we are not that much involved into the affective part, but we are mainly involved in what we call the cognitive evaluation. For example, when you think about, okay, what others are thinking to do or what are the traits that they are experiencing, we are talking about the cognitive evaluation. So we are not talking about what do they feel, or I'm trying to feel what they are feeling and trying to have a sympathetic kind of relationship or empathic relationship with them. We are talking about cognitive aspects of reading their minds. And that would get other areas involved in terms of, as you can see here, this part is related to the affective processing, that they have mid-cingulate cortex involved, insular cortex involved, right and left insular cortex. But when they had cognitive parts, they had more, let's say, dorsal anterior cingulate cortex, and then some other components in other parts of the brain. But there are still some overlaps as well. So the yellow one would be areas that would be overlapping as well. Okay, so this kind of dichotomy of affective and cognitive might be something that could be a little bit helpful in terms of understanding these processes. But it is not super helpful. I mean, we know that they are, most of the time, they are combined to each other. So they work hands in hands to be able to give us an understanding about these processes. The other component of this process that is definitely important is what we call an area that is called superior temporal sulcus. So we have superior temporal sulcus, we have inferior temporal sulcus, and it seems areas around superior temporal sulcus they are critical in terms of social cognition, and how they are critical for that. People realize that different sorts of social cognition or social cognitive components would activate these areas around superior temporal sulcus. And probably this one is the most important one, biological motion. And biological motion is just those really simple movements that give you a feeling that, I mean, these movements are related to a biological agent or somebody who has a level of intention. And this is something that I mean, people have done different studies in terms of even defining, okay, if I have just simple dots in the screen, how can I just move these dots to give people a sense that these dots are human agents, or these dots have a specific intentionality? And people realize that if you make those figures, make those movements that make a level of intentionality compared to the movements that are not really intentional, if you show people kind of these two sets of pictures, they have a specific activation when they see things that are related to specific biological motions, and their activation would be in superior temporal sulcus. And if you remember from what we have discussed about in previous session, this part of the brain is involved in what we call the secondary visual processing, and we can perceive motions. But it's not just motions. We also have memories of other motions, and we are able here to be able to compare these memories with what we have. I mean, what we already have, the movements that we are perceiving right now, the movements that we perceived before, and see whether there is any sort of intentionality or a level of, let's say, agency in these movements. And that is why the reason that we have superior temporal sulcus involved in the intentionality process. And that is probably one of the most important part of the social cognitive processing. Okay. Let Let me give you another example of social cognitive process and another social cognitive task. This task is about having just a joint attention and solo attention. So probably I do not have enough time to get into the details in terms of how we can compare joint attention with solo attention inside fMRI scanner. But we can give people experimental design to give them joint and solo attention. So having a shared attention with another person, we both are looking to something, or you are just alone looking to something, comparing these two conditions to each other. If we just subtract joint from the solo attention, these are the activations that you can see. Okay. Obviously, you can see activations here in the medial frontal gyrus, probably in areas related to, let's say, ventromedial, posterior cingulate, areas here in the parietal, parieto-temporal junction. Still, this is this superior temporal sulcus, so you can see this is located here as well, and there are activation in cerebellum as well. So these are the activations that you have. Okay, so this is the activation that you have. But sometimes it's just really complex because you have activation in different parts. You know that there are different, let's say, cognitive processes that are involved. But it's really hard to say which area is involved in which cognitive process. Okay, to be able to do that, people have done what we call hierarchical clustering. Clustering. And by hierarchical clustering, what do? They consider all these areas, and they put them in something like a table, and then they measure the level of correlation that these areas, let's say this area to another area, the level of correlation that their activity would have to each other. For example, as you can see here, these areas, these three areas in the bottom of this, they have highly correlated to each other. First of all, these two areas are really correlated to each other. So the algorithm work in a way that the algorithm put these two areas together, because it seems that these two areas are highly correlated. As you can see here in the matrix, they have a high level of correlation, whatever these two areas are. Okay, and if you see in the matrix, these two areas are correlated. As you can see here, the color shows the level of correlation. So the more reddish you get, the correlation would be higher. So we put these two areas together as well, and then we look for other areas. For example, these two areas, they are also correlated with each other significantly. They put them together. So the algorithm would start to put together areas and realize that what would be the minimum level of correlation that they need to get to a one cluster. And if we just proceed with this process of clustering and putting them together, we will end up with a threshold. I'm not going to discuss about how we get to this level of threshold. And if we get to this level of threshold, if we just cut in this level of threshold, we have three clusters: cluster 1, cluster 2, cluster 3. And if they just put different colors on these clusters and just put these colors over the brain, you can see that technically they have one network in the red areas, and then one network in the green areas, and one network in the blue areas. Can you name these three networks for me? The blue network, the green network, and then the red network. If you want to attribute a specific name to these three networks that are being made by what we call an unsupervised machine learning method, trying to put clusters or areas that are more correlated to each other in the same cluster, and trying to put areas that are related to each other to the same cluster, and areas that are far from each other away in different clusters. This is called unsupervised machine learning method, which we are using here as something like what we call hierarchical clustering. And this is a really simple machine learning method. Those who are doing machine learning process, they know that is super simple initial steps of doing machine learning processes, unsupervised learning processes. But if you want to kind of define those, let's say, networks, and network 1, 2, 3, red, green, blue, what would be the name of 1, what would be the name of 2, what would be the name of 3? This is exactly the level of expertise I really like you to develop in terms of understanding the names and trying to see the areas and trying to differentiate them and having an understanding about the distribution of these areas. Red might be DMN. Okay, good. Very good, very good. Yeah, that is a really good, I really like the answer that you provided. Obviously, the blue one is visual. The red one is DMN. And the green one is sort of ECN or frontoparietal part. And as you can see here, these are the medial side, PCC for DMN. And these are the labeling that the textbook or the kind of the red K team provided. They call it attention control, social cognition, visual network. We already have people from the machine learning side here. I'm not sure if Rahim is with us today. And we also had some others with machine learning background. Could they turn on their videos and let us know that they are here today or not? I think that Venus is also doing machine learning studies. Anybody else who has a machine learning background? There's also there without being in pajamas, being able to turn on the video. Okay, it seems that our machine learning people are not there. But yeah, you can see how, technically they have done this job and how they have been able to do this, let's say, bringing this machine learning method to the process. So that's another level of, as you can see here, why do we have these, both networks involved? Why do you think that? It's quite amazing that when we talk about joint attention, it is not just about the central executive control or kind of attention, the executive control network, but it also includes a significant level of default mode network contribution. So you can see both networks are contributing to this process. Why we have both networks involved for joint attention? Anybody who's interested, just turn on your videos to see how many people are interested to discuss about that. Mikhail, do you want to share your experience?
Well, I think both networks are needed because if you, in social interaction, focus on only one aspect in communication, you're not able to see the person as a whole. So you need to keep an open flow, yet while processing very precise information. So I think both networks have to be mobilized.
Absolutely. And you technically need to have both in terms of understanding what is happening inside you and referring to what is happening inside you as something like doing a self-referential processing, and also understanding what is happening outside. So you need to have both your extroceptive network and your introspective network to be able to have a sort of shared attention. So without having both networks involved, you cannot see inside yourself and then seeing others outside and communicate through the shared attention without having both networks involved. You need to have both processes involved to be able to do that. And it's beautiful to see that even a completely non-supervised, blinded machine learning method would be able to differentiate these networks into clusters. So differentiating them in, let's say, visual cluster, executive control network cluster, and default mode network cluster. We just knowing about the data without having any idea about, we have a default mode network and executive control network. Just with having the data, the machine learning method would be able to differentiate them into these clusters. And that is this is really good. So it is sometimes it's not, I mean the data is not. Sometimes it's really hard to say it's good, too good to be true, but it is definitely too good. I mean, it is not always the case that you can have this really good differentiation into, let's say, neuroscientifically interpretable results in a way that you can just have really good clusters and really good, what we call a decree graph in terms of having a good GNU to be able to define the good point for kind of differentiating things. As I told you before, that it is not, it is something like a spectrum. So it is not just 0, 1 or black and white. That okay, I mean we have one on, the other off, the other on, the other off. So it is not the case. So these are the options that, I mean, when you want to bring both into a process, you can do that, but you need to allocate your resources between both, which is not probably the most efficient way of having the processes in one of those processes. But sometimes it happens. Sometimes you need to have both involved to be able to do the process. Otherwise, you cannot. You cannot basically do whatever you need to have. The other probably wise way that they have done the processing, so they included the data from just the activations that they had. So they limited the space that they were doing the clustering within the space. So it is not just something like the activation in the entire brain. It is just activation in some few limited areas that they had significant activation. So they extracted data from the limited space of significant activations. And then, I mean, the results was pretty much meaningful in terms of having these clusters. So that's the reason that we need to have people from different disciplines contributing to this process.